Hi guys, we're gonna pick up where we left off yesterday. So we had just finished up with molecular compounds. I'm gonna do a quick recap of the difference between the two types of compounds, and then show you some ways to identify, when it's ionic, when it's molecular, and do the corresponding name or formula. And then we'll jump into the chemical reaction stuff. So first thing is ionic compounds involve ionic bonding. So that's an important thing to know, because with molecular compounds, the bonding name is not the same as the compound name. So ionic bonding, whereas molecular compounds, it's covalent bonding. So that can sometimes cause some confusion. So we're going to just recap the main key differences and then tackle a few examples. So with ionic bonding or ionic compounds, the types of atoms involved are generally a metal and with a non-metal, but it's a little more inclusive to say a positive ion with a negative ion, right? Because that then allows us to incorporate polyatomic ions, right? So just know that lots of times it's a metal with a non-metal, but it's really any positive ion combined with any negative ion. Whereas a molecular compound there's only one way to do it, and that's a non-metal, plus another non-metal. So two non-metals. Now, the difference between what's happening here in these bonds, like the bond is really always involving the valence electrons. In an ionic bond, the positive ion gives electrons, I'm just going to put E negative, to the negative ion. Right? So there's actually a transfer. For example, sodium gives its one valence electron to chlorine so that they can both have full outer shells. And that actual transfer of electrons makes the one that gives it away positive and the one that accepts it negative. Whereas in covalent bonding, which results in a molecular compound, the electrons are shared between two atoms. In ionic compounds, we never ever use prefixes. No mono, no di, no tri, none of that. But in molecular, yes we do. In ionic compounds, we do use Roman numerals. So we'll say yes, but not every time. Only for ions with multiple charges. Okay, whereas in molecular, nope, never use a Roman numeral. And finally, overall charge of the compound. This is kind of getting at that crisscross situation. So in ionic compounds, positive charge equals negative charge, right? You're always making sure positive equals negative, so you get a neutral or an overall charge of 0 in the end. Whereas in a molecular compound, when they share their electrons, there really is no charge. There's no ions. So we'll say charge is irrelevant. Okay, now on to the chart. So when you're looking at compounds, you'll either be given the name or you'll be given the formula. And by looking at them, you have to decide, okay, am I dealing with an ionic substance or a molecular substance? Because that's going to dictate how you give the formula or how you make the name. So the main thing you're looking at is what types of atoms are involved. Here I've got sulfur and I've got oxygen. Both sulfur and oxygen are nonmetals, so that would be my first indication that this is molecular. The second one is, well, a shortcut would be, do I see a prefix, a tri, a di, a tetra, one of those things? If I do, then it is in fact molecular. So both of those things lead me to choose molecular. So molecular ones are easy. No charges to think about. Sulfur, one of those. Oxygen, 3 of those. Done. Now, if you look at the formula, you don't have like the prefix or lack thereof to rely on. You have to look at what types of atoms are involved. So I see sodium and I see chlorine. Sodium's a metal, chlorine's a nonmetal. Sodium becomes positive, chlorine becomes negative. So that's an ionic compound. And when I name an ionic compound, I just name the first element and change the second one to IDE. And then I'm just always got my eye out for whether or not they need Roman numerals. Another thing to look for is the ate ending or the ite ending. That indicates a polyatomic ion. Polyatomic ions are only involved in ionic compounds. Okay, so same thing here. Well, first of all, you've got a metal. Anytime you start with a metal, it's going to be ionic. But you know there's a polyatomic ion here because there's more than 2 elements involved. So that's going to be an ionic again, right? So just keep your eye out for those little tips and tricks and go through and label them as ionic or molecular and then give the corresponding name or formula. Okay, so you can go back and finish this after the video. Another thing to look at that you would have learned last year is balancing equations. So let's just pick something to balance here that maybe we'll pick this guy down here. Okay, so when we balance an equation, what that means is that we're coming up with sort of like a recipe for the chemical reaction. We're looking at what ratio do these things react in and what ratio are the products in. So we're looking to put, sometimes we don't have to put anything in here. They just it's all a 1 to 1 to 1 to 1 ratio. But in many cases, that's not the fact. And that's because you have to ensure that the number of atoms of each type are the same before the reaction as they are after the reaction, in that you can't have atoms disappearing. Like you can't just have iron, you can't start with 2 iron and end with 1. That would indicate that 1 iron atom vanished into thin air. Okay, you also can't have more atoms over here than what you started with, because that would indicate that some atoms just appeared out of nowhere. Like, where did they come from? So whatever you started with still has to be present after the reaction, okay, but it's just been rearranged into a different format, right? They've just regrouped themselves to make new products. So what you can do, there's a kind of a few strategies. You can make yourself a little chart. Lots of people like making a chart. Okay, so you can make a reactant side and a product side. And you can take an inventory of what you have. So you've got iron, you've got oxygen, and you've got carbon on the reactant side. And I'm going to make that same list on the product side. We still have iron, oxygen, and carbon. Now I'm going to count up. Remember, this is the 2 sides. This is the reactant side. This is the product side. So on the reactant side, I've got 2 atoms of iron. There's 3 oxygens here, and then there's another one over here. So that makes a total of 4, and there's 1 carbon. If I look at my product side, I've only got 1 iron, I've got 2 oxygen, and just 1 carbon. Okay, so if I compare the start of the reaction to the end of the reaction, nothing lines up. I've got 2 iron to start, only 1 to end. 4 oxygen to start, only 2 afterwards. The only thing that stayed the same was carbon. I started with 1 carbon, I ended with 1 carbon. So in order to make this true, to make this actually reflect what would actually happen, I need to mess around with how many copies of each substance I have to make each side balance. So my starting point probably would be to balance out the iron. So let's try putting a 2 here. So what this means is I'm saying, okay, I'm going to produce 2 copies of iron, okay, so that I can up this from 1 to 2. And I can say, okay, I started with 2 atoms of iron, I ended with 2 atoms of iron. So that looks good. Okay, but I started with 4 atoms of oxygen, and over here I only have 2. So in order to make this reflect like the law of conservation of mass, which just means you can't create or destroy matter, I could put a 2 here, right? Because that would mean 2 times 2, that's 4 oxygen. Okay, so oxygen now checks out. I start with 4, I end with 4. Nothing's been gained or lost. But by putting that 2 there, I also upped the carbon. Now I have 2 carbon, but I only have 1 over here. So that's a bit of an issue. So now I have to go back over and fix carbon. So I can put a 2. So now I fixed carbon. But what did I do to oxygen? Well, I just added another oxygen. So I went from having 4 to now having 5. Okay, so what can be done there? Well, that's never going to quite work, right? Because if I go and up the oxygen on this side, the only thing I can do here, the next multiple of oxygen I can make, I'm now at 4. The next best I can get is 6. Okay, so let's try 6. So that makes 6 oxygen. Now I'm at 3 carbon. Okay, well, if I go over here and change this to 3 to match the 3 carbon, let's see if that fixes the oxygen as well. 3 here and 3 here. So that makes 6. So the point of balancing is to ensure that you have the exact same amount of every type of element before the reaction as you do after the reaction. And you can only change how many copies of each substance you have. So you can only put numbers in front. This is saying I have 1 copy of this added to 3 copies of this, and that's going to produce 2 copies of iron and 3 copies of carbon dioxide. So it's like a recipe, right? Like you'd have 1 cup of flour plus 3 eggs and so forth, right? So this is like our chemical reaction recipe. I need 1 of these, 3 of those in order to get 2 of these and 3 of those. And that ensures that all my atoms are conserved. Nothing's lost, nothing's gained. So the trick with balancing is that there's not like a step 1, step 2, step 3 to follow. Sometimes it's a little bit of trial and error. You've got to plunk some numbers in, and sometimes you have to go back and change them. So like if you do something like this one here, it's a little bit easier. There's a little less, some are hard, some are easy. So just to show you a little bit easier one, if we looked at zinc plus oxygen producing zinc oxide, if I take a quick inventory, I'm going to split this down the middle. On the reactant side, I have 1 zinc and 2 oxygen. On the product side, I have 1 zinc and 1 oxygen. So the only way to make 2 oxygen is to put a 2 zinc oxides. But that changes both zinc and oxygen. So I fixed oxygen. Now I need to go and fix zinc. Good. Okay, so that one's much easier to balance than something like this. And that's quite common. Some are easy, some not so much. Okay, if we take a look at reaction types, I'll just remind you of the reaction types that you looked at last year. So I'm going to kind of give you a general formula for each one and see if you can match them up to the examples over here. So the first type of reaction we looked at in grade 10 is called a synthesis reaction. So synthesizing something means to create something. So a synthesis reaction follows the formula A plus B produces AB. So the idea is that you take two simpler elements or two simpler compounds and basically they combine to make one product. Okay, so a synthesis reaction is fairly easy to identify because it's the only reaction that has only one product. So as soon as you see a reaction where there's only one product on the right-hand side, you can be pretty sure it's a synthesis reaction. A decomposition reaction is the exact opposite. So synthesis means to create, decompose means to break down. So we're just going to take that synthesis reaction and flip it. We're going to take our compound and we're going to break it into simpler pieces, break it apart. So you can always recognize a decomposition because it's the only type of reaction that has only one reactant, only one thing on the left-hand side. Then we'll do combustion next, and then we'll do the two types of replacement reactions. So a combustion reaction is a reaction where something is burned, it's combusting. So in a combustion reaction, they're easy to recognize because they have the same repeated components. And those components look like this. A combustion reaction always has to have oxygen reacting. Everything that burns requires oxygen. And the products are always carbon dioxide and water, CO2 and H2O. The only thing that changes is the fuel. The fuel is made of carbon and hydrogen in some, like these X's and Y's change, but it's always a compound that contains carbon and hydrogen and sometimes oxygen as well. So it could also have oxygen mixed in here, but at the very least it contains carbon and hydrogen. So these three things are always the same in a combustion reaction. Now over here I'll do the displacements, or you can either call it a displacement or a replacement reaction. So there's single displacement. I'm just going to shorten that. And there's double displacement. Okay, the idea is the same. A single and a double displacement both involve a switch, but it's just the nature of, or the way that switch works or looks is a little bit different. So in a single displacement, you've got an element, so something that's not a compound, like just say pure copper or pure oxygen, or like it's not combined with any other element. So you've got an element plus a compound, and the element switches places with something in the compound. Okay, so it's going to switch with what it's most similar to. So if A is a metal, it'll switch with a metal. So in this is an ionic compound. It's always metal, non-metal. So if A is a metal, A will switch with B. So B goes by itself, and A and C make a compound. Okay? If A was a non-metal, A would switch with C, and then you'd get C by itself, and B and A would make a compound. So the switch can be different depending on what A is. So you always look to A to see how the switch is going to happen. So it could be A switching with C to get C plus B A. So there's a switcheroo going on, and really you look to your element to see what that switch is going to look like. In a double displacement, you have two compounds. So compound AB plus compound CD, and they just switch partners. So the easiest way to remember how they switch is it's always a positive one from one compound with a negative one from the other. These are always ionic compounds. So the outside ions get together, A and D make a compound, and the inside ions get together. So it would go C, B. C being the positive one, B being the negative one. So it's two compounds that switch partners. Here it's an element in a compound, and the element switches with one part of the compound. So use those to see if you can identify which type of reaction is which. There is, I think, one of everything. Yeah, there is one of everything. And some of these will also require some balancing. Not all of them, but some of them need to be balanced. Okay, the last thing that we're going to do is we're going to look at reaction, like writing reactions. Okay, so I'll do one from each section with you. This is supposed to be, what did I screw up here? Solid magnesium plus hydrogen chloride. Oh, this is supposed to be chlorine gas. Okay, so let's do this reaction here. Or maybe let's do the second one. Never mind. Okay, so solid magnesium. Basically, the point here is you're going to turn this sentence into a written chemical reaction. So what you have to do is you have to go one substance at a time. So I'm starting with magnesium. Magnesium is just an element. And I'm going to include states: solid, gas, aqueous, or liquid. So you're familiar with solid, liquid, and gas. If you didn't learn about aqueous last year, aqueous means dissolved in water. Okay, so the other way that that's sometimes phrased is it'll be called a solution. A solution is something that's been dissolved in water. Okay, so when I see that it's solid magnesium, I put an S there for solid. Okay, where were we here? Sorry. So solid magnesium, I've got magnesium symbol and the S for solid, reacts with, I can just use a plus sign, hydrogen chloride. So I want to examine this and see, okay, is this an ionic or a molecular substance? So, well, hydrogen's a bit of a tricky one because it's actually, in reality, a non-metal, but it sometimes acts like a positive ion. So, because I'm not seeing any prefixes, there's no mono or di or tri or anything like that, this would be an ionic compound. So if I look up hydrogen on my periodic table, it has a positive 1 charge. Chlorine has a negative 1 charge. So I can write that compound like this, HCl. And then I see the word solution. So for solution, I use the symbol AQ. It's been dissolved in water. To produce, that would be where I'd insert the arrow. And my next compound is magnesium chloride. So I should also check, this is no prefixes, metal, non-metal. So I'm going to look up charges. Magnesium's a positive 2, chlorine's a -1, so I'm going to crisscross magnesium chloride, again, solution, and plus chlorine, oops. Oh, I did fix that, never mind. That was supposed to be hydrogen gas. Right? Yeah, sorry, I used to have the wrong word there, but I must have fixed it. Okay, so hydrogen gas is H, and hydrogen is a Hofbrinkel. So remember that acronym means that if any of these guys are found alone, they will be diatomic, H2, and then G for gas. So that is really, I'm just taking the name and turning it into a formula. And then once I've got it all laid out, I'm going to go back and balance the equation. So if I kind of do a quick inventory, I've got 1 magnesium on each side. I've got 1 hydrogen, but I end with 2. So I'm going to fix that right now. I'm going to put a 2 here. I also made 2 chlorine, but it just so happens that there's 2 over here anyway. So that balanced the entire equation just by putting that 1 number in. The last thing I could do is I could recognize that this is a single displacement or single replacement reaction because there's an element and a compound, and magnesium and hydrogen swapped places, right? Hydrogen got bumped out on its own, and magnesium joined up with chlorine. So we can also do the same thing. We can go the other way. We can go from the balanced equation into a sentence. And I always urge you to keep your sentence very, very simple. Like, don't try to make it fancy. So if I were to do this guy here, I would just start, okay, I'm dealing with aluminum. It's solid. Solid aluminum. And then for the plus sign on the reactant side, I always just say reacts with. Now I've got a chemical formula, so I have to decide if it's ionic or molecular, so whether I need to use prefixes or what. So copper is a metal, chlorine's a nonmetal, and copper happens to be one of the ones we highlighted. So we want to put a Roman numeral, copper chloride, and I'm going to insert the word solution just so I don't forget. Okay, now I want to figure out what Roman numeral goes in here. Well, chlorine has a -1 charge. Remember, I'm going to separate my negative side from my positive side, but there's 2 of them. So over here I have -2, so that must mean copper is +2. So I'm going to put Roman numeral 2 there. Solid aluminum reacts with copper 2 chloride solution. For the arrow, I just say every time to produce solid copper, and all you need to say is and for this plus sign. And here again, another ionic compound. Aluminum's a metal, chlorine's a nonmetal. Aluminum does not need a Roman numeral. Aluminum chloride, solution. And just for the grand finale, that is, again, a single displacement because the aluminum and the copper switched places. Okay, finally, we're almost done here. The last thing you can do is you can finish a reaction, okay? So I'll do 1 or 2 of these, and then you'll have to rely on the little bit of notes we made about reaction types to help you with the other ones. So here I've got chlorine and potassium bromide reacting, and I'm told it's a single displacement reaction. So that means that I look at my single guy, chlorine. Okay, so I'm looking at chlorine to figure out, I know there's a switch happening. So what's chlorine going to switch with? Potassium or bromine? Well, chlorine's a nonmetal. The nonmetal in this compound is bromine. So those 2 guys are going to switch places. So I'm going to rewrite the reaction. So the first part stays the same. Now, if I want to switch chlorine and bromine, that means bromine is now by itself. So bromine is also a Hofbrinkel. There's the br in Brinkel. So you need a 2. That's why chlorine has a 2 as well, because it's in Hofbrinkel. Okay, and potassium is now going to join with chlorine. So you have to look at, well, how would it join together? like it's an ionic compound. So potassium's a +1, chlorine's a -1, so you just need 1 potassium and 1 chlorine. Just because there's a 2 here doesn't mean you're going to plop it in over here. Just like here, bromines, there's just 1 bromine, but over here there's 2. So that's why we have to go back and balance. So the 2 on bromine makes me put a 2 here. And then I can also put a 2 here to balance out potassium and chlorine. So these are probably the trickiest. You have to think of the most things all at the same time. However, if you just do it slowly and carefully, you will figure it out. So you just really have to think about your reaction types, and you have to remember how ionic compounds are formed, and just avoid that tendency to carry subscripts over from the reactant side to the product side. It doesn't always work like that. These are completely new substances over here, so you treat them separately from the reactants. Look at them as something entirely new. This bromine needs a 2 because it's a Hofbrinkel. These get together 1 to 1 because potassium's a +1, chlorine's a -1. Okay, so another easy one to do, if you were doing this one, your products are going to be the outside ions are going to make a compound, the inside ions are going to make a compound. Here, combustion, you always know what the products are. Go back and look at our notes. We outlined that combustion always has the same 2 products. Then you can just balance it. A decomposition is just going to take this compound and break it apart. Watch out for Hofbrinkel. And a synthesis is just going to join these guys together. Just remember that when they join together, you have to look at the charges they have as ions to make the formula. Okay, so you can finish that off, and then there's some extra practice for you to do when you're done.